Complex engineering problem. Performance of transmission lines and cables. Topic: design of submarine power cable of offshore wind frame. Presentation by Ketavat Suresh. Presentation roll number 23951A0224. Department name Electrical and Electronic Engineering. 5th semester. Content of the presentation: problem statement, objective, overview, requirement, prerequisite, solution to the problem statement, result, analysis and conclusions. Problem statement: power and signal transmissions line and cable must deliver electrical energy or data reliability, efficiently and safely over the distance. Performance and can degrade due to losses. Evaluate and design the transmission line and cable system to meet a required power capacity of signal integrity, minimize losses and distortions, ensure the thermal and mechanical robustness, and comply with relevant standards. Objectives: characterize electrical performance matrix, attenuation, impedance, capacitance, inductance, progressions, delay, dispersions, crosstalk, returns loss, quantity losses and thermal limits under the expected loading and environmental conditions. Identify and mitigate cases of signal degradations, reflections, EMI, corona dielectric adoptions, providing designs and selections guidelines for cable and transmission line for power and data applications. Overview: transmission line, overhead lines, underground power cable, coaxial, twisted pair overguides, PCB trays, and optical fibers are characterized by distributed parameters, series resistance, series inductance, shunt capacitance, and shunt conductance, often expressed of per length unit. These parameters determined characterize impedance, progression, constant phase velocity, attenuation, and dispersions. Requirements: general. Define the applications: power transmission, HV, EHV, medium voltage distribution, short power runs or signal data links, broadband, RF, digital. Require the capacity, rated current and voltage, power or bandwidth, bit rate data. Environmental constants: temperature range, humidity, UV exposure, corrective atmosphere, burial depth, reliability and availability target. SAIFI for utilities, be a packet loss for data system. Requirements: electrical measurement parameters, performance of target, maximum allowed the voltage drop or lines losses, power percentage losses, maximum allowable attenuation dB by km or iterations losses at design, the frequencies, returns losses, VSMWR limits for RF digital to ensure the reflections are within the budget, crosstalk and next facts, limits for multi-phase cable or adjacent lines, maximum allowable temperature range and amplicity rating. Requires knowledge of transmission lines theory, distributor parameters, models, technologies, telegrapher's equations, understanding of material properties, conductor conductivity, skin effect, proximity effect, dielectric permittivity, and losses the tangent. Thermal modeling basics for amplicity calculations, access to manufacture data sheets, cable specifications, and soil installations parameters. Simulation tools. SPICEM field solves HFSS CST lines, parameter calculators, or power flow tools for grid level lines. Solution to the problem statement. Model. Modeling transmission line parameters. Calculate for unit length RLCG RF. Include DC resistance and frequency dependent increase for skin effect and proximity effect. Use conductor geometry and materials conductivity. Compute AC resistance using the analytic formulas for or EM solvers. L. L. Based on conductor geometry and returns path. Include the internal and external inductance. C. Function of conductor spacing, dielectric permittivity and geometry. G. Dielectric losses from loss tangent and leakage path. Compute the characteristics impedance Z0 under root R plus j omega L by G plus j omega C and propagation constant gamma equals to alpha plus j beta under equals to under root R plus j omega L into G plus j omega C. Second thing, loss analysis. Attenuation alpha due to conductor I square R and dielectric losses. Convert to the dB by km per signal lines present loss for power lines. Account for the radiation losses in properly shielded system or waveguidance at a high frequency for power lines. Calculate real power losses. P losses equals to I square into RAC distributed over length. Include corona and corona loss module for HV lines. Thermal ampacity calculations. For power cable, compute the ampacity using IEC 60287 based on install method, soil thermal resistivity, ambient temperature and conductor temperature limits. Thermal steady state equations. Heat the generator I square R must be dissipated. Result analysis. Key metrics to measure and reports. Attenuation installations losses dB by km or dB at frequency measured versus calculated. Characteristics impedance and impedance uniformity measured with TDR. Return losses by VSWR across the operational band. Propagation delay and group delay flatness. Disruptions. PS Nm into Km for power losses and thermal rays. Ampacity validation under the steady state and an emergency duty. Conclusion. Performance of the transmission lines and cable is a multidisciplinary engineering problem that the combining electromagnetic theory, thermal analysis of mechanical designs and practical installations of considerations accurate modeling. RLCG per unit length for the materials and the geometry selections and the preordained mitigations, shielding, filtering, equalization, cooling, surge protections. Thank you.